Solving systems of linear equations by substitution. So we know that the solution to a system of linear equations is some ordered pair that makes both equations true, which means we can use our equations to work together to find that solution. Okay, so the first thing you want to do when solving by substitution is have one of your equations have a variable isolated. So looking at that second equation, we already have y by itself, which means we can take what y equals and replace the y in the other equation with that expression. So we're going to replace the y in the first equation with 4x. So we're going to have 16 plus, and then we substitute in 4x for y equals negative 4x. By doing this, we are working with one variable. So now we solve for x. So we want to get all the x's on one side. So we're going to move 4x to the other side. So that simplifies to 0, leaving us with 16 equals negative 8x. Okay. And then we now need to divide both sides by negative 8. And we get that x equals negative 2. Now remember, when we're trying to find a solution, we know it's some ordered pair. So we know our x coordinate. How could we figure out our y coordinate? Well, let's just substitute it back into one of the equations. It does not matter which equation you choose. I'm personally going to pick that second one, because it has a little bit less to deal with. So now I'm going to be substituting in negative 2 for x, because that's what x equals. So y equals 4 times negative 2. Substituting that negative 2, 4 times negative 2 gives us negative 8. So our solution to this system is negative 8. One way to check yourself is to substitute in those coordinates into both equations. Because remember, if it's a solution to the system, it should make both equations true. And so here we get 8 equals 8. So it works for that first equation, but it needs to work for both. And this is something that we just did, so we know that it works there. So negative 2, negative 8 is our solution to this system. Okay, now let's pause the video so you can try this next one. Okay, so here we're trying to solve by substitution. We want a variable isolated. We already have it right there in our second equation. So we're going to take 3x and substitute it into the other equation for y. Again, we're using the equations together, meaning if this y is 3x, this y is also 3x. So let's see what that looks like when we substitute it in. Minus 3x. Notice how it did not replace the negative sign, it just replaced y equals negative 6. And then combining those, we get negative x equals negative 6. So x equals 6, because there I just divided both sides by negative 1. Okay, so that's the x coordinate of our solution. How do we find the y coordinate? Well, let's just substitute 6 into one of our equations for x. You can pick either one. I'm personally going to pick that second one because it's a little easier for us. So y equals 3, substitute in 6, so y equals 18. Remember, you can check this solution by substituting in your coordinates into both equations to make sure it makes both equations true. Okay, so here works the same way. We're trying to solve by substitution, so we want a variable isolated. We have y isolated. So we are going to substitute in this entire expression into the other equation for y. Notice it's just y. It's not the y term. It's only the y variable. So we have 5x minus 4. And when I substitute in, I like to put it in parentheses because that me that that -4 affects every single term in that expression. Okay, so now that we're working with one variable, we want to solve for x. So we're going to start by distributing that -4, okay? So we can bring down that 5x, and let's distribute. -4 times -3x is a positive 12x. Remember, distribute it to every term in that expression. -4 times 5 gives us -20. And now we want to simplify. So 5x plus 12x. Remember, that's just 5 plus 12 to give us 17. And when we combine like terms, we end up with a like term. Okay, now let's isolate our x terms. We want to add 20 to both sides. When we add 20 to both sides, that leaves us with 17x equals 17. Last step, undo that multiplication with division to get x equals 1. Okay, now that we have our x coordinate, we need our y coordinate to complete our solution. So we substitute in 1, since it's telling us that x is 1. Let's look back at our system and substitute in 1 either here for x or here for x. Either way, you're going to get the correct y coordinate. I'm personally going to use that second one. So we're replacing the x with 1. So we're going to have y equals -3 times 1 plus 5. And then we have -3 times 1 is -3. -3 plus 5 is 2. So our y coordinate is 2. Remember, we can check that. That ordered pair should make both equations true. Okay, so let's pause the video for you to try this one. Before we can solve a system with substitution, we need to have a variable isolated. And our first equation already has that y isolated, so we can use that to our advantage. And remember, when we're solving a system, we're trying to find that ordered pair that makes both equations true. So we're trying to find the intersection point, the point that both lines have in common. So that's why we are going to use them together. So we're going to replace the y in the other equation with our expression. Okay, so we're going to have 3x plus 2 times 5x minus 7 equals 12. And then we're just going to solve for x. We can combine like terms. We want to move 14 to the other side, so we're going to add it to both sides. And then lastly, divide both sides by 13. Okay, so now that we have our x coordinate to be 2, how can we find the y coordinate? Well, we're just going to use substitution again. We're going to substitute in 2 into one of our equations for x. You can pick either the first equation or the second equation. I'm personally going to use that first equation. So we're going to substitute in 2 for x. And so then we have y equals 10 minus 7 gives us 3. So then our solution is the ordered pair 2, 3. So something to think about. What about systems of linear equations that have no solution or have infinitely many solutions? What happens when we solve these systems algebraically?